On behalf of my co-authors, Professor Robert Gao, Professor Jürg Kruger, and Professor Joseph Wanza, I would like to present this year's STC-A keynote on human-centric assembly in smart factories. Evolution of industrial assembly was influenced by the evolution of manufacturing paradigms. Over time, there are different manufacturing systems, but also influence assembly systems. From the beginning, it's a craft assembly, gradually moved to mechanized assembly system, then automated. More recently, we talk about human-centric assembly. But why we need human centricity? We think, looking into the future, we need to preserve our own basic value. Our personality, we have ideas, we have beliefs, we have curiosities. Those are very fine qualities that really drive us to think more. Based on that, human has a creativity, ingenuity, and innovation. Collectively, it forms our vision. Most importantly, dignity. Our human's existence, our ownership, job satisfactions. Without human, those things cannot be done. Human, as the most flexible integrators, cannot be replaced by AI, by machines. Thinking about in the future, manufacturing assembly operators. This is the operator in the future, a human. We don't have a strong muscle strength. We cannot compete with a robot. What can we do? We can use augmented robots, for example, exoskeleton, to help us energize ourselves. So over time, our muscle will not be too much experience fatigue. Normally, we make decisions based on our perception. However, what is going on in the next room, we don't know. But if we have a cognitive system, like a multi-agent system, to help us collect all the information around us, we have a holistic view. We can make global optimal decisions at all times. We use our 5 senses to observe the world, use our seeing, hearing, and so on. But sometimes we want to see what is invisible. If we use augmented reality, we can see something invisible. This is very helpful for the human operators. We can use also digital twin, send it into the near future to explore what is going to happen. Then digital twin will tell us with more precise prediction in 5 seconds, 5 minutes. AI is very powerful. Perhaps we can combine our very human intelligence with artificial intelligence. In this way, 1 + 1 is greater than 2. Human can tell robot what to do to train them. Robot can help us to do easy job. We can also use our brains to control robot. Just like a control robot, robot is our third arm. We can control both arms. Why not control additional arm? This can be controlled by our brain after training. Use a large language model. Then we can apply our knowledge, our experience to do human-centric assembly, supported by augmented robots and based on real-time situation. So the aim for human-centric assembly is to ease the human task. You watch the movie Mission Impossible. Ethan Hunt or Tom Cruise, using smart devices, can accomplish impossible missions. In the future, the human can do the same thing. The mission impossible for manufacturing today will be possible tomorrow. We also need to work together as a team. If the team work together, we can realize both sustainability and resilience at the same time. For this keynote, we have 5 different objectives. Because of time, I will not go into read them, but those are written in the keynote paper. We need to enhance human capability increase safety, ergonomics, worker satisfaction, and job increase. Humans' role in the future will be context-aware data acquisition, state inference, training, teaching, explanation, and recovery. That's our job. State system influencing through decision-making and actuation. The keynote is divided into 10 chapters. I will focus on the technical part, also identify the future challenges and directions. First of all, what is a human-centric smart factory? We consider a human-centric smart factory would not only introduce advanced technology to factory floors, but also consider personalized complementary skills and situational preference. This would be a smart factory with a human in the center. We already have a different enabling technology along the production line, assembly line. But eventually, critical decisions need to pass on to the human to make. The decision is critical. Otherwise, can be automated by computers or robots. The future operators may take different shape. It can be in these 8 different forms, supported by different enabling technologies. Let's go through some of them as an example. Super strength operators, like exoskeleton. There's 2 types, basically, passive and active. Here listed 4 passive systems from different companies, different countries. There are also active systems. By active, it means motorized. Let's take a back exosuit as an example. When we bend down and raise up, we use our muscles in the back and the leg and following the joint in the hip. This device uses the same principle. However, there's one challenge. It's the alignment of joints. If the joints is not aligned well, we don't feel comfortable. Or if I'm bending down, the motor try to pull me up, we cannot do the job. So there's some challenge there, use advanced sensor technologies. AI is very powerful, and it is needed to be supported by some other tools like VR, AR, and MR. I'm sure you all know, quite familiar with this. I will skip this part. But supported by AR, we can do the job with human support on the fly, on demand. This is one example. Augmented operator supported by AR. Use this smart goggle. We can specify the start position and specify the trajectory, use our finger gestures. Eventually, in this case, brake can be laid up one by one. This is a typical type of assembly, but the same technology can be applied to manufacturing assembly as well. We can use a digital twin to help us, I mentioned earlier, to send a digital twin into the future to explore what is going to happen. Assembly task or robot execution takes some time, a few seconds or a few minutes. During that period of time, digital twin can explore what would be the optimal parameter given the current situation and simulate this trajectory is the best, also considering external situations like obstacles. If it's good, send it to the robot to do the operation, otherwise redo it in the digital world. We can use artificial intelligence to help us to process different data. In this case, it's the brainwave signals. That can be processed as well, use a different enabling technology, as mentioned in the reference. Eventually, the command can be retrieved from the hidden pattern and tell robot, this is what you need to do. Large language model is very popular these days. Use a camera to shoot around an object it is possible to create a 3D object in very short time. And use a mobile robot with an arm, it is possible to navigate around with good perception and cognition. If we pass this information to the large language model, it can basically, based on the scene, context, and our human instruction in language to do the job, generate robot control code. From natural language to robot action, several steps must be followed. Tokenization, understand the natural language, logic reasoning, supported by large language model, control logic generation, and high-level control code generation. All this, even today we have many different large language models. They need to be anchored and mapped into a world model through foundation model. This is very important. Do not lose the context. So this is just an animation how the command from natural language is eventually passed to a robot. The next topic is how to use our brainwave to control the external devices, to control robot. If this can be done, we can control robot in close distance or in remote mode. However, human brainwave can be divided into different frequency range. However, during the daily operation, it must be in the frequency range from 13 to 100 hertz. We don't want the operator to fall into sleep. And so this is the range. The rest will be filtered out. We use our brains in different ways. Everyone uses brains differently. Brain can be divided into chiefly 4 different regions. And based on whether you use language, use memory, use your vision, different part of a brain will be activated. And that signal will be retrieved. Based on this, we can do the analysis. However, thinking involves several parts of the human brains. We cannot know for sure everyone uses the same brain at the same time today and tomorrow. There's a change in the morning, in the afternoon. Our brain will be influenced. This is one challenge. Holding a single thought over several seconds is challenging. We tend to think something else. Focus is difficult, especially difficult in a factory setting. There's noise surrounding. How to analyze the data is also another challenge. Normally we do is use EEG, electroencephalography, to collect information, pass it onto the computer to do signal processing, and eventually we can control the robot. There's different ways to control the robot or process the brainwave signals. The simple way is to consider 3 different patterns in one sentence: subject, predicate, and object. Very simple grammar. We pass this brainwave in the waveform to the computer. It contains 3 parts or 3 words. We call it the control words. And then this waveform is converted to time frequency images and through continuous wavelet transform. We can have more information digged out in the later. Because CNN is very good in processing images, we pass on these TF images to the deep learning model. Eventually, we can figure out what I'm silently thinking in my brain is actually robot pass screwdriver. That command will be sent to robot through function block. Function block contains internal algorithm. The internal algorithm based on information received and also some other information dynamically collected from sensors to modify the decision algorithm to generate a different result adaptively. Eventually, a native control code can be generated. This is a topography of our brain. Eventually, when brainwave collected, it shows like this. Some part is active and shifting to another region. And TF image are generated. This keynote also identified 10 challenges. These challenges of future research directions can be divided into 3 different groups. We use a color code to group them, the red part, green part, and the blue part, and with a different geometry shape. Because of time, I will talk about number 3, challenge number 3, foundation models for natural human-robot interaction, and also explain number 8, new safety standards for human-centric systems. You may wonder what's the relationship between the 10 different future research directions. This is their grouping, their relationship. We summarize it into a table. The top shows the level of organizations. It could be relieve, delegate on the top row, or could be augmented, extended. The last one is inclusive and integrated. In terms of technology capabilities, it's listed in the first column to the left. It can be used in design, building, validation, system configurations, and can be used for planning, optimization, integration, interaction, and learning at different levels. In terms of anticipated impact, it shows in whether it's a dark black or thick line circle or black, or it's a thin line boundary. The first example, number 3, foundation method for natural human-robot interaction. If we apply this future research direction to the layer or row 3 for interacting with the environment, sensing, calibration, and actuation, their role is average in the thick line. If we apply the number 8 future technology research direction to on new safety standards to the last column, and then their impact is different. On the first 2 rows, they can generate a major impact, but the 3rd row or 4th row is average. We also wonder, how long does it take the roadmap into the future? This is a really challenge for the team. The starting point we know, but the ending point we can only guess. So this chart is normalized from 0 to 1. 1, everything is finished, achieved. And the technology, the shape, is similar to the technology group in the earlier slides. Some of the technologies need to be further developed. Some are already in dark line, dark shape. That's quite mature, but some not there today. We need to pay more attention, and hopefully sometime into the future, we can start to develop that and consider they are relevant to the manufacturing assembly. Because of time, I will stop here. Thank you very much.
Thank you very much.